All right, calculus, we are looking at AB 45 exponential growth. The growth that goes like this or like this. Gets really big really fast or really small really fast and then kind of keeps getting smaller or it keeps getting bigger. All right, let's take a look at it. So the idea is the rate of change of some quantity y is directly proportional to y. You hear this in calculus. It happens. So when we're talking about rate of change, let's talk about rate of change. That's really saying something like dy dt. And it says it's directly proportional. So what does directly proportional mean? That means that it's kind of like a constant. It's multiplied by a constant. That's the idea. Constant. Constant. So what winds up happening is the quantity, some quantity y, the rate of change of y, which is dy dt, are directly proportional. They're multiplied by some constant k. So you wind up getting this piece here. This is the big idea. And then you kind of move on from there. It's like, well, what if I were to solve that differential equation? What would happen? Well, here's kind of the process it goes through. You separate the variables. You get the y with the dy, and the antiderivative of y is natural log of y, and the other side is just k times t plus c. Then you got the absolute value of y is e to the kt plus c. But hey, this is kind of interesting. The absolute value, e to raise to any power, is greater than 0, so you don't need the absolute value. It's gone. Then we have y equals e to the kt times e to the c, because it's really like two factors, and then write e to the c as a new constant, so e to the c is really c, and blah blah blah. You get to this right there. Now some people write it like this last step. I usually stick to the step before that. But really the big thing to consider is that constant, when you say y equals c times e to the kt, consider t equals 0. If t equals 0, then k times t equals 0 as well. And e to the kt is equal to e to the 0, which is equal to 1. So at time 0, y equals c. So this c, this is your initial value. That's really what's going on here, initial value. All right, so what's the big idea with all this? Know it forwards and backwards. You got to know that this and this are tied together like exact. And notice here it might be a little bit easier to solve for the k, whereas here it's a little bit easier to solve for the c. So let's translate some as an example. All right, punctured tire. We got a punctured tire. So it says write a differential equation. So that tells me I'm going to say something like dy dt. It states that the fact that if the pressure is 35 pounds, so that's the pressure, this is my quantity. It's not, it is changing, but it's a specific value. It's not a measure of the rate of change, it's just the pressure. That's my quantity. So pressure, to me, is really equal to y. Okay, and that's 35. And it's decreasing at a rate of 0.28 pounds per square inch per minute at the time the nail is struck. So wait a second, you put a nail in a tire, so that's the time the nail is struck, that's the beginning, that's like t equals 0 there. And right here, a rate of 0.28, that's saying that dy dt is 0.28. So dy dt equals 0.28 when y equals 35 and t equals 0. Okay, so what's the big deal then? Is that it? Is that really all it is? Well, this is the big deal. Directly proportional. They're talking about directly proportional. The rate of change is directly proportional. So that tells me that dy dt is going to be k times y. So I know that it's 28, but knowing that it's k times y, and I know y, I could figure out k, which we're about to do here. So it says solve that differential equation. We know that dy dt equals 0.28. We also know that that is equal to k times y. Okay, no big deal. Let's keep going further. We can go further by saying, well, if 0.28 equals k times y, we know what y is, so 0.28 is equal to k times 35. Ooh, now we're getting closer here. Let's see what we can do with that. I need my calculator. Let's warm it up. I'm going to divide both sides by 35. And we're going to get something from that. Let's see what we would get. So hopefully at this point you guys are starting to use your calculator and beat me to the answer as it warms up. That's going to give me k. Okay, so I can figure out what k equals with that division. Here we go. Calculator. 0.28 divided by 35. 0.008. So k equals 0.008. All right, that's half of it. Here's the other half. So the other half, you got to consider that y equals a some constant times e to the kt. And this constant was your initial value. Well, in this case, that initial value was what we started with. Well, let's take a look at that. The initial value was 35. That's my initial value. That's what the very first value for the quantity was 35 pounds per square inch. So C equals 35. So what is the actual equation? Well, now that we know K and now that we know C, we would have, drum roll please, Y equals 35 times e to the 0.008. That's my K, T. So I have a function. That is so cool because now I can plug in T and figure out Y, which is what they want me to do here for part C. So if I know that Y equals 35 times e to the 0.008t, what would I do with that? Well, I would start by saying Y equals 35 times e to the 0.008 times t, which is 10. I could calculate that because I have a calculator. So I'm going to do 35 times e. Well, e is right here above the division symbol, so I got to do second e to the, and then we have 0.008 times 10. Well, that was easy. 37.91504. Something does not seem right. What was it? 37? What did I get? 37.915. Well, let's take a look at what's happening here. Maybe I entered in something a little bit wrong. So I'm going to graph this. I'm going to graph this relationship, see what we got. We would have 35 times e, so we got second, oh, you know what, maybe I should have done this, e to the, instead of the other one. 0.008. And then we got our variable, which in this case is an x, even though in our other writing it's a t. And we're looking at 10 minutes. So let's just go from like 0 to 10 minutes. That's fine. And this is probably going to go a lot higher. So we'll start with 0 and we'll go up to, let's say, 40. What do we got? So there's our graph. So something's going on. And I know what's happening here. And it has to do with one little word. There's an error in here. Why does that go up? Well, it should be going down. This means that the rate is not 0.28, it's really negative 0.28. And because it's negative 0.28, that means that this right here is negative 0.28. That's a negative. and then we divide by a negative. This is going to be a negative 0.008, which means this is going to be a negative, and this is going to be a negative. So let's see what our value would be this time. So I need to recalculate this, but put in a negative in front of that 0.008 because it's decreasing, not increasing. So I'm going to do second, insert, and then negative. Now it's decreasing. Check this graph. We're going down. So we're here at about 35, and then we're going to, well, what's this at about 10 minutes? I could calculate that value. So I'm going to do second calc. I just want a value, number 1, at x equals 10. What do we got? 32.3. So this is wrong. 37.915, that's wrong. And 32.3 is what we want. So y equals 32.3. I know there's more decimals than that. 3090. 3090. Check. No problem. The car is safe to drive as long as the pressure is 12 pounds per square inch or greater. For how long after the puncture will the car be safe to drive? Okay, so what I want to do now is I want to graph another line in here. So I'm going to go to y equals, and I want to graph the line 12, because as long as I'm above that value, then I'm good. So if I take a look at this graph, look at this. I am above this value, no problem. Nail in my tire, no problem. But it looks like it'll eventually go down. So maybe I need to expand this a little bit. So let's look at my window. Instead of going to 10 minutes, let's go to a full hour. That would be 60 minutes. Now instead of counting by ones, I'm going to count by fives. Similarly, for the y scale, I'm going to count by fives as well, just to make it a little bit easier to count. Let's look at my graph now. So there's my time. This is after 1 hour. Whoa, look at this. I'm still good after 1 hour. It looks like I need to go to 2 hours, which would be like 120 minutes. There we go. So now, here's 2 hours worth of time. Ooh, I am still doing just fine. So, I'm going to go even further. Let's go to 3 hours. That would be, how much would that be? 180 minutes. Hopefully we intersect this time. We do, right here. Where is that? When do I drop below 12? Because once I drop below 12, I'm screwed. Flat tire, accident, really bad news. So when does this happen? Well, I can calculate that intersection. So second, calculate intersect. And it's pretty close, but let's get it really close. Here we go. Right there. That looks good. Okay, so now I do it, enter 3 times, and it says at 133.8051 minutes. So 133.8015 minutes. Is it 1.5 or 5.1? 5.1. 5.1. Let's erase that, rewrite it. Minutes. That's just over 2 hours. It's like 2 hours and what, 13 minutes, 14 minutes? So about 2.25 hours. It would be safe to drive. But honestly, don't do that, people. Don't just say the math said it was safe to drive. If you run over a nail, go get it taken care of. Like now. Pull over. Do something. Don't drive. That's just silly. But the math said it was okay. Alright, let's look at another example. Bacteria in a lab culture grows. Alright, this says grows. Why am I highlighting that? Because that was an issue in the last question. It said decrease and we thought positive. But grows means dy dt is going to be greater than 0. It's going to be a positive. In such a way that the instantaneous rate of change, that's the dy dt, of bacteria is directly proportional to the number of bacteria present. So y equals number of bacteria. Alright, no big deal. Write a differential equation that expresses that relationship. That means that dy dt equals k times y. Check. Solve the differential equation for the number of bacteria as a function of time. Okay, so what that means is it's asking us to really solve this equation. So let's pull this over, and if we have dy dt equals k times y. I need to get the dt up, so I'm going to multiply this up here. Then I'd have dy equals k times y times dt. Now I got to match y with dy, so let's get that over there. Once we're at this point, now we're ready to integrate. We're going to integrate both sides. So the natural log of y is going to be what we get on this side, absolute value, of course, equals on the other side k times y. No, k times t. kt plus c. All right, once you're at that point, now you can start trying to get these things by themselves. So we're going to have absolute value of y equals e to the kt plus c, kt plus c. And then we drop the absolute value because it's really positive since it's e to a power. Then we can split this up. E to the kt times e to the c equals y, because then y equals c, initial value, times e to the kt. That was it. No big deal. Okay, so we're ready. We got to use that. Let's use it. Ready, set, go. Suppose that initially, oh, that's talking about the initial value. There are 5 million bacteria. That means that C equals 5 million. 3 hours later. Okay, now we got some information here. This is saying 3 hours later. That means that when T equals 3, if we're talking in hours, the number has grown to 7 million. So when T equals 3, Y equals 7 million. Write a particular equation that expresses the number of millions of bacteria as a function of hours. All right. So that to me says that I have y equals c times e to the kt. Well, I know that c is 5. We're just going to say it's in millions. Times e to the kt. No big deal, right? Okay. And when t is 3, y is 7 million. So that means that 7 equals c times e to the k times, well, what do we got here? 3k. Okay, that's not too bad. We also know that y equals 5 when t equals 0. And that, oh, this is not a c then. So let's shrink this down. And that constant we already figured out. That was 5. Well, this is kind of interesting. Because since I knew that 3 hours later it was 7 million, and I knew that the initial value was 5, I've narrowed this down to one variable. I could solve this. Check this out. So what do I want to do? I got to write a particular equation that expresses number of millions of bacteria as a function of hours. So for me to write that out, I need to figure out what k is. So how do I figure out what k is? Well, I do some math here, some algebra. I divide both sides by 5. That gives me 7 over 5 equals e to the 3k. All right, at this point, I'm going to look at natural log, because if I take natural log of both sides, that gives me natural log of 7/5 equals 3 times k. So now I'm going to multiply both sides by 1/3. And that gives me 1/3 natural log of 7 over 5 equals k. That's just awesome. Am I going to have enough space for this? Yeah, it looks like we are. Okay, so let's work it out. From this point, so that's a value. That's going to give me a value. Let's calculate that value. So I'm going to do 1 divided by 3 times natural log of 7 over 5. 7 divided by 5. Here we go. Ready, set. It is 0.1121. So k, whoops, take that back. K equals 0.1121. What do I do with that? Well, I can plug that in here now. So that tells me that y equals 5 times e to the 0.1121 t. Sketch a graph of time versus bacteria over 10 hours. So here's 0, here's 10. Let's graph it. So I'm going to go to my y equals. Take out this one and this one. We know that k is 0.112, so when we put all this together, that equation that's in blue is complete. So we're going to have y equals 5 times e to the, so I'm going to do second natural log, e to the 0.1121 times the variable. We're going to use x in this case, even though it's t earlier. Then we go to our graph. What do we got? Oh, that's kind of off the page. Let's take a look at this for 0 to 10 hours, which is really just the beginning. So window, oh, we don't need to go to 180. Let's go from 0 to 10. Let's see what we get there. Oh, that's fine. That's no big deal. We can even cut this down. We can go to maybe, let's say, 20. We're going to count every one. We're going to count delta 1. Delta y is going to be 1. There we go. Let's graph it. Oh, that looks great. Look at that. Doesn't that look great? That looks so good. In fact, I'm going to just copy and paste it. That's wonderful. So let's copy and paste this here. Boom. Oh, from 0 to 10. Let's stretch it this way then. 0 to 10. There we go. All right, so what's my range here? This was 0. This was 20. That's how high I went. That looks pretty good there. Sketch the graph of time versus bacteria over 10 hours. Check. Let's move on. What will the bacteria population be 1 full day after its first measurement? Okay, so 1 full day really means that time equals 24 because it's in terms of hours. So I got to calculate 24. All right, well let's take a look at that. We go to our calculator. We have to go from 0 to 24. That's going to be huge. 0 to 24. All right, we're already off the screen, so we got to increase this quite a bit. Let's go instead of from 0 to 20. How about 0 to 80? And we're going to skip by tens. Does that give us enough? Ooh, just barely. So after 24 hours, it looks like we're up here around 80, maybe 75. Let's calculate it. How do I calculate? Second, calculate value. When do I want to calculate? I want to calculate it at 24. When x equals 24 hours, or when t equals 24 hours, what's the value? 73.68. So I'm going to copy and paste this into here as well, because that's kind of doing the same thing that we were looking for. There we go. So the answer, 73.687 million. All right, last question out of this group. It says, when will the population, in other words, that's the y value, when will the population reach 1 billion? Okay, let's think about how 1 billion compares to what we're talking about. We've been talking about millions, and 1 billion would be equal to 1,000 million. So because we're doing this in terms of millions, let's try to calculate 1,000 million. So I got to graph a line here. I got to graph the line 1,000. Well, let's graph that line. So I go to y equals. I got to graph the line 1 billion, which is really 1,000 million. Now when I go to my graph, it is nowhere even near that because the top of this is at 80. So I have to go all the way up to 1,000. Let's look at my window. I'm going up to 1,000. But you know what? I'm going to go slightly even higher than that. So where were we? Oh, the custodian came in and interrupted. But anyways, here we're looking at, we got to go all the way up, not to 80, but we're trying to go up to 1,000. So let's go up to 1,000. But you know what? Let's go up to like 1,010. just above it, so that we can at least see it. Now, we can't really count by tens to 1,000 because that would be 100 little marks all the way up here on the screen. So I'm going to count by, let's say, hundreds. All right, and it's probably going to go beyond 24 hours, so I don't really know how long it's going to take. Let's say 50 hours. Let's see what we get. So now I'm going to graph this. Let's see what happens. Whoa, look at this. That's crazy. So down here, it's way low. And you're thinking, that doesn't seem that low. Well, 100 is this first mark. And after, what's this, maybe 15 hours or so, we're not even barely off the line. But talk about, not even more, just a little more in 2 days, we are way up there. So I'm going to take this picture. And this top line here, up here, across the top, that's the 1,000 mark. So that would be not just 1,000, that's really 1 billion. So that's 1 billion bacteria. That's a lot. So I got to calculate when these two things intersect. Let's do that. So second calculate, then we're doing intersect, and it's a lot. I'm going to guess 47. What do you guys think? Maybe you already did this. Oh, that looks a little too far. That's good. So second curve, close enough. Guess. And it looks like, hey, look at that. I'm right on. 47.26. So I'm going to bring this down so we can annotate it a little bit. Move this over. So what are we looking at? When does it actually equal 1 billion? When does the bacteria equal 1 billion? It's right there. Right here. When does that happen? That happens at 47.26420. So when T equals 47.264, Y equals 1 billion. Or 1,000 million. So there we go. That's what we got. And that's really all we have for you. Just a couple of examples showing how to use this information to work backwards into finding some predicted values. Like when are we going to reach a value and what will it be after a certain amount of time. Crazy. Alright, so that's it for this video. Happy stars to you, and we will see you in the other one, number 47, is it? 47. No, 46, Exponential Growth Part 2.